is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light. And I've heard others call from light years away. And they're real, and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's home. Boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars. And I've heard others call from light years away. And they're real, and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Well, hello everybody, and welcome to SkyTour live stream. It is I, Mark D'Antonio. Nice to see you all. Early crowd coming in tonight. That's wonderful. We have plenty to do, plenty to see. It's kind of cool. I do want to say hello to the folks that have come in early. We've got Tiffany. Tiffany's with us. Hi, Tiff. We have Daryl, of course, and if you haven't heard of Daryl, well, here he is. Hey, Daryl, how are you?
Hello, Mark. I'm good. How are you? Hello, everybody.
I'm fine, thank you. And then we have Tim F., who's woohoo. He always says woohoo when he comes in. Tim, you're losing your edge. Usually you're the first one in, you know. And then we have, of course, Suzette. Yay, how are you, Suzette? Nice to see you. And Daisy and Zoe Amethyst, good evening to you as well. Daisy and Zoe will sometimes bring in their cousin Lane. And Lane is interested in astronomy, but she's apparently not around right now. But that's okay. It's good to see you, Donald Kunzer. Good to see you. And Red Angel, what's going on? Red Angel, what's it? Red Angel Lover Dollar Sign. Okay. Nice to see you, man. Catherine Messick is with us. How are you? And I am about to start up. We have this object right we're looking at right here. Let me show you what it is. I'll annotate it for you so you can see. This is the Blaze star. This is the star that's going to be going supernova sometime in the next few months. And,
Nova.
I mean, that's what I meant. Yeah, Nova, thank you. In the next few months. And that differs from a supernova. That's what I was in my head. I was going there, and my brain got ahead of me. A nova is different from a supernova. A supernova obliterates a star, leaving behind a neutron star or a black hole. And a nova is different. It can recur, and the reason it can recur is because of the nature of how a nova is constructed. And how that works is we have a red giant star, which is a star that has actually reached the end of its lifetime. It's near the end. And what the star does is the star will actually swell to a giant state, a giant red giant state. And as it does that, it may have a companion, okay, that's next to it. And it could have been two normal stars orbiting each other. But then what happened was one of those stars aged before the other, and we ended up getting a situation where we had a red giant and a white dwarf at the end of its stellar existence if it goes to a white dwarf. And white dwarfs are stars like the sun and slightly more massive. That'll happen, with a star the size of the sun or slightly bigger. It'll go down to a white dwarf at the end of its existence. And so you have the red giant, and the red giant's massive, and then the white dwarf might be orbiting it very closely. And if that's the case, then as the red giant swells as it approaches the end of its life, it can bleed hydrogen gas onto the surface of the white dwarf. Now, a few things can happen there. A situation can occur where so much hydrogen gas goes onto the surface of the white dwarf that its mass gets tipped past a magical point, which is 1.44 solar masses. If that whole white dwarf is 1.44 times the mass of the sun, then that'll create an obliteration situation where the white dwarf will obliterate itself in what's called a type 1a supernova. However, in the case of this star we're looking at right here, the Blaze star, you'll notice it's slightly red, and that's because we're seeing just the red giant, which is massive here compared to the white dwarf. In the case of this situation, the white dwarf isn't the mass of the sun, or 1.44 times the mass of the sun. It's something less, so that when the hydrogen bleeds onto its surface, there is a point where the hydrogen can get hot enough to spontaneously fuse in one massive conflagration. All right, and when that happens, we get this immense brightening of that star, and that's the nova. That's what happens at that point. So that said, we're waiting to see it happen, and it could happen, and it will happen between now and say 2025. So we're gonna watch. We're gonna watch.
Can I make one note on that?
Of course.
As far as the white dwarf goes, it's not necessarily at the end of its life. If it does eventually go supernova, well, it will be. But otherwise, that white dwarf can last for billions and billions of years as a white dwarf.
That's true, because white dwarfs take a long time. Now, what's going on in a white dwarf, though, just so people understand, in stars, the power supply is nuclear fusion, otherwise known as nucleosynthesis. Atoms and nuclei, rather, that are in the core of the star are pressed together so hard from heat and pressure, okay, that they will form a different atom. So hydrogen is squished together to make the next element in the periodic table, which is helium. And that happens all the way up to iron, which is number 26 in the table. We have 118 elements. So you might wonder where all the rest come from, but that's another time. But that process of nucleosynthesis is something that is the power source of the stars. However, in a white dwarf, That's not happening. Okay, a white dwarf's not undergoing fusion of any kind anymore. It's a collapsed core of a star. It retains a lot of heat, and that heat won't dissipate, as Daryl says, for billions and billions of years. And I think that's why white dwarfs, we still see plenty of white dwarfs out there. And so the nuclear fusion process is done. So the star is no longer a star per se. It's a bright spot that we can see, but it's not a star that's actively undergoing fusion like all the rest of the stars that we know of. So in this particular case, we will see an ongoing, as Daryl said, potential for another nova, another burn off of the hydrogen that bleeds onto the surface of the white dwarf. In this particular star's case, it happens every 80 years or so, and we're there now. So, and it's sort of plus or minus some months, so this star right here could go nova tonight as we're watching it. And all of a sudden it'll get extremely bright. And we'll say, whoop, guess what we caught? And we'll mark the time, and we'll report it to the International Astronomical Union and other sites, and let them know that we caught it at the moment it went, and then send the imagery that we have. But the likelihood is that because it's so unpredictable, that right now, if you look where the telescope's pointing that way in the the building out there. That's toward the west, okay? And I'll show you by, let me just take care of getting rid of our annotation right now. We'll come back to it. Okay, if you look up here, this is our telescope's position. It's pointing right there. That's the western horizon right down there. See that? This western horizon is where this constellation is setting, and it's going to keep going down toward the northwest and west-northwest as the night progresses. At some point, it'll be below the horizon, and now as the Earth keeps going around the sun, this constellation, Corona Borealis, will not be something the Earth is facing at night anymore, and it's going to be on the day side. So there's a possibility that this nova could occur, and we'll never see it because it'll be happening during the day. Now, radio telescopes could pick up the nova, and if there's if a radio burst comes from the nova at the time, or some other energy, and so that's the kind of thing that radio telescopes would do, because they operate night or day. Okay, I built a radio telescope, and we use it all day long to study Jupiter's moon Io. So it's pretty cool. So while it's here, while it's up in the evening, we can check it out. So this is the star right here, and you might wonder what that is. Okay, that's actually a satellite that's tumbling, and notice this dash. That was the next thing. This is a tumbling rocket body, so that's why it looks like a dash. Right, as it tumbles, when it's facing us like this, it's really bright, then it tumbles like this and it's less bright, then it tumbles like this and it's bright again, and it does that. And so the distance between these gaps is exactly the same, because there's nothing to speed it up or slow it down out there. It's going to continue going. It's not hitting any it's not going to hit any particles at that altitude. It's actually quite far away, because this dashed line shows us that it's quite high up. This might be 500 or 600 miles, but it's glinting. Now, how would I know that? Because we're doing a 4-second shot right here, and in 4 seconds it goes that far. Okay, so we would, from experience, I know that the length of the line to be in orbit, the lines get shorter the higher the orbit is. A Starlink satellite would have gone across this entire view in the 4 seconds, right? Because it's only a couple hundred miles up or so, but this satellite's much higher, and it's taking, quite a number of seconds to even cross here, So I want to say hi now too. Let's see, we have what's that? I saw someone else here. Oh, that's C Brown 19. Hey, how you doing? Thank you for joining us. If you haven't subscribed, please do, because you know what? We're cool. We have a great time here. Michael Hedrick's with us. Michael, what's going on, brother? C&D boy from Canada, he's here. How you doing, man? And Keith Evans. Hey, Keith. How are your binoculars? Keith won binoculars from us in one of our giveaways. And let's see.
Izabela's here.
And Izabela's joined us. Hello, Izabela. Yeah, that's a very pretty tumbler. She's right. Yeah. And C. Brown is asking, are you able to see Comet Bernardinelli Bernstein? And I don't know, Daryl, can you check that? It's 2014 UN 271.
Yeah, give me a minute.
Okay. All right, we'll check on that in the background. If we can, maybe we'll take a look at it. You'll notice this little red in here. That's because we're still getting a little bit of the sunset leftover light. Even if you can't see it with your eye, it's there because our camera's very sensitive. So once again, before we leave, this right here, in the middle here, this is that star that's going to go nova. It's known as the Blaze star. Has quite a history because it has gone nova before. All right, and so when that red giant bleeds that hydrogen gas onto the white dwarf, every 80 years, that hydrogen gas gets to the density and temperature such that it can spontaneously fuse. And when that happens, the whole surface of the white dwarf blazes up in intensity. Much brighter, even brighter than the brightest star in this constellation, which I will show you right now. This is Corona Borealis as we back out here. It'll be even brighter than Alphecca, which is right here. And Alphecca, if we look at it, its brightness is 2.2 in magnitude, we call it. And the nova might be even brighter. So we might see a new star in the sky for a very brief few days, and then it'll be gone. So pretty cool.
Bernardinelli Bernstein is presently 2,367,570,000 kilometers from Earth. It's a long ways away.
Yeah.
This is the really big one that they've noted for a couple of years is on its way in.
Yeah.
Some information I saw a little while ago is, let me see, when was perihelion? I think it was in 2031.
Yeah.
And it's presently due to magnitude, almost magnitude 18. So we might catch it, but it won't look like anything. And magnitude 17.92. I mean, that's quite dim.
Yeah.
Telescope might catch it, but it won't look like much.
Yeah, it won't be very exciting. But this is the Blaze star right here, T Corridor. We're going to save this right here. And I'm running on a lower sensitivity, which I'm going to give you a little tour of that right now. So you guys see what that means. All right, so for instance, all right, if we look at the screen here, this area right here, this is the telescope control. All right, so all these parameters in here control the telescope. This is the telescope computer. You'll actually see the screen. You'll see what it's looking at and what kind of data gets transferred back and forth. You'll see that. This is obviously the scope in the building, two different views. This is, well, you know who this is. That's me. And since we're actually taking an active photo, we're actually stacking. We're creating an image sandwich. So we're taking an image, aligning it with the previous, and stacking images on top of each other. And that reduces noise and makes for a far, far better image. Okay? And then this is the camera control system over here. Okay? This is all camera control. The most important values here are the exposure here and the gain here. So this is the sensitivity of the sensor on the camera, and this is how long we're going to expose that sensor with that sensitivity. Now, you play off these two numbers because the lower the number, the less digital noise you get in the image. Okay? And the higher the number, the more noise you get, but the more you can see. So you play off. You try and do a little bit of, either way, So, that said, this is the tour. This is our annotation screen, by the way. This floats around, which is why I didn't address it. Okay? And this tells us all the things that are in the screen. So if I get rid of it, they just go away for a moment. Okay. All right. Yep.
The comet also, it's far down in the southern sky right now. It's not visible from us, for us.
Okay.
It's like 34 degrees from the South Pole.
Okay. That's quite far. They may show up in our northern hemisphere at some point. Got to look at its path and see what it's going to do. Yeah, so this is great. All right, so T Corona Borealis, we're doing this primarily because Izabela asked for it. Izabela, in our chat, you can see her in there. She's literally one of the people that helps keep us going, helps make us tick. She's wonderful. A lot of talents. And so she's actually, asked for this particular image because she likes to do comparisons of previous images to current images. And she's seen what we think are asteroids in some of the previous shots. So it's pretty neat. Hello, James Hyatt. What's going on? Asher, how you doing, man?
Yes, the comet will be at perihelion in 2031.
Perihelion is closest to the sun.
Oh.
Okay.
Looking for information when it's close to the sun.
Mm-hmm.
Interesting. Comet's orbit is nearly perpendicular to the plane of the solar system. One reason it's so far south.
Mm-hmm. That means you could go really high in the north.
This is true. I don't see anything offhand about where it will be in 2031.
For those wondering, this planetarium program is called Stellarium. It's free. You can download it. I have a paid version because we want to make sure we get a lot of cool add-ons to help see what we're doing, and a lot of extra stellar catalogs and so forth, which are free as well, by the way.
Can I talk about something real quick while you got the star map up there?
Yeah.
Can you show Scorpius?
Oh yeah, that's way down here.
Yeah, you had Ophiuchus just a minute ago. It's just below Ophiuchus. Okay, there's the Scorpion. He's a little bit west of south right now. And I've mentioned before, Scorpius is the southernmost of all the zodiacal constellations. And so it comes and goes the quickest of all of them. And it's in decline now. But I've mentioned this in the past, maybe on a radio show when I was on there. This time of year, something interesting happens that I've noted again this year. At this time of year, as summer is waning and it's getting dark a few minutes earlier every night, if you tend to go out and look at the sky at the same time every night, Scorpius and the bright star Antares, its heart, tends to kind of hover and hang in the southwestern sky. This is because it's getting dark a few minutes earlier every night that, well, it appears to pause and stay in the same part of the sky for a while. And if you watch the sky every night about the same time, go out after sunset when it's just dark, you can see Scorpius do this. It'll sort of hang in the west for a few weeks. Then all of a sudden, bang, it'll be gone. Neat thing to note this time of year.
Yeah, absolutely.
And if you go out and look on the clear evenings after sunset, as I tend to do, you can see it up there right now. Antares is real bright in the south-southwest. And Dashuba, its forehead, is the bright star just to the right of Antares. And then over at the other end of the Scorpion there, those two stars that are close together, that's the Scorpion's stinger at the end of its tail, and they're called Shaula and Lasaph. And they're also known as the cat's eyes because they're close together. Mm-hmm. And you can see the cat's eyes over to the left of Antares. That's all. Thank you.
No, that's cool. Thank you. I'm going to see as Michael Hedrick was saying the volumes need to be up a little higher, so I'm going to try and do that. This might do it. I'm not sure. We're going to find out. Hang on. Modify. 1, 2, 3, 4, 5. Okay. That's a little better. Yeah, I think that's better. And you're still good, Daryl?
Michael Hedrick said, I'm fine. He says you're the one that's quiet.
Yeah, I know, but you're still good. I'm just making sure you're still good. And you are. Okay.
I guess.
You are. Okay. Now let's see here. Alright. Okay, so, anyway, I'm going to take us up now to where I was just a moment ago. This is the summer Milky Way down here, by the way, and we may come back to that, but I want to show you this beautiful stellar pair right here. This stellar pair is something that I have visited many, many times. I'm going to save the blaze star one more time, like this, and then I'm going to save exactly as seen. All right, and then I'm going to come out of this. And we're going to go into our low light mode that we use to look at objects as we're heading out to look at them. It helps us to see our view. This is the view I'm talking about. And I will also get our system online there. Now you can see the lit up area there. Okay, and so now let's go and come back into here, and let's go to Albireo. You'll watch the telescope. Going to head straight up and look toward the back side of the observatory. There it goes. And we should see Albireo come into the view. You'll see two bright dots come into the view here shortly. And there they are. All right, so let me work on this for a moment here. Let's see here. How about this? Is this better? Oh, I think this is better. Yeah, I think this is better. Okay. Thank you, Izabela. All right, so I'm going to bring us up now, and we will see now that in here you see these beautiful pair of stars. This is really pretty here. Oh, yeah. Hey, James Dugan, how are you? Nice to see you, man. How are you doing down in Australia? I hear Daryl typing. Okay, let me just pull us a little to the west here. Okay. Alright, so this is Albireo. It's a K-type star with a B-type star. The K is a star. Let's go and show you. It's a K star that's actually a giant star. Let me show you the spectral type here. It's a K3 2, that Roman numeral 2. The K3 means it's a little bit from K0 to K9. It's 1/3 of the way, roughly through the K stars. And then the other Roman numeral number, which you see right up there, right here actually. Where's the spectral type again? I just had it right there. That number right there. Okay, K3 and then the Roman numeral 2. That tells us that is a luminosity class. The luminosity class is how bright it is intrinsically. All right. And so this is a big star. And then we have next to it in the sky a B-type star, but it's almost an A-type star. It's a B9. So we have O, B, A, F, G, K, M. Right? And so we have O, B, and this is not a B0 or a B3, but it's actually a B9. So it's almost to the A0 level, but it's still a blue star. And its luminosity class is a Roman numeral 5, V. Okay, 5. Which means that it's a normal fusion star. It's actually making hydrogen into helium in its core. So that's it right there. And what we'll do now is we'll go into our deep sky mode, and you'll still see them there, but this points out the colors very nicely. Look at that. Look at those beautiful colors. Those are real. All right, we can actually kind of just bring that up just a tad, so you can actually see that. Look at those colors. Very blue and very orange. K-stars are orange. Okay. Boy, it'd be so cool to be in space to see these up close. That'd be something. So anyway, let's try and do a quick stack on these. We're gonna actually do just a 5-second shot, which is 5,000 milliseconds, which is why I'm putting 5,000 in up there on the right, up here. All right. I'll start this photo and then go into our live stream. Our live stack, and we'll stack it. And you'll see the previous thing we had. I'm going to clear that buffer. And next thing you'll see is we will have our Albireo shot. You'll notice that Albireo is actually blowing out of the water. It's blowing out with the brightness, and we can change that. We can affect that and make it look better. So one thing I'll do is I'm going to take this. We're going to go just to the left here. And then I'm going to take this mid-range here, and I'm going to move us way down. Okay, and you'll see it's going to look a little better now. Way down. All right, look at that. So now you see the orange and the blue, and you see them in the context of the stars around them, and this is going to show you a little better. Let me color correct here. I'm just going to do a color correction. Now, you'll also notice that in this region of space, you're going to see reds, and you're going to say, uh-oh, I guess that must be the sunset still. But no, actually, in this region, we're in the summer Milky Way. That's why you see so many stars. There's actually a number of red nebulae in this area. If maybe we're only doing a 5-second shot, so we may not see it, but I'll try it. If we punch it up, you can see that there's some red out here, and there's some red nebulae in here. Now, we don't usually punch it up, and we're actually only taking a shot at 150 sensitivity. All right. Normally, we shoot at 200. But look at this beautiful shot. Isn't that pretty? That is just really pretty. So I'm gonna actually store that like that. That's gorgeous. We're gonna save that shot. Now, where are these shots going? When we save these shots, well, these shots will go up to the server as we're taking these pictures. You see it's being saved. So as an example, I'm going to click on this and you'll see the photo. This photo right here of Albireo that you see right here. This is actually going up to our server. And when you go up there in about, I'd say 35 seconds, this photo will be waiting for you and you can download it. So all the photos are free. All right? If we do this real special processing, well then we will, we hope you'll join our Patreon to get those. All right, but you get this shot right here. That's free. So we do offer free stuff. Anyway, and Izabela just put out the server. That's great, and so did Daryl. Thank you both.
Michael Hedrick has a question for you.
Okay.
It's kind of off topic.
Hey, Jay Blaine, how are you? On my phone, all you see is little dots, LOL. Yeah, well, compare that to the people that are actually watching this on their large screen TVs, some of them with popcorn. Hey, Sam S. Let's see. We see... I'll get to you in a moment, Michael. It's actually... It's not a K9 star, Michael. Silly. It's a K2 and then Roman numeral 2. All right. But that's funny. Yeah. Lewis asks, is that a binary? It's a visual binary. They may not actually be close to each other, but they might just be line of sight. And let's go now and check out Michael's question. What did he ask? I missed it. I'm trying to find it.
Mark, another question, please.
Oh. Do you know how many gravitational fields astronomers use when calculating the orbit/trajectory of any particular individual sky object? Well, yeah, they use all the gravitational fields of all the nearby substantial gravitational tugs that they get from planets. As you can imagine, when you're studying asteroids and when you're studying other things, minor planets, and especially the near-Earth objects, you have to account for the gravitational tugging caused by the Sun primarily, Jupiter secondarily, and then Uranus, Neptune, and Mars, Earth, Mercury, and Venus, kind of in that order. And then, of course, the other asteroids that have insignificant but potentially significant gravity as you add it all up.
Don't forget Saturn.
Yeah, that's right. I didn't mention Saturn. You're right, Saturn. Yeah, Jupiter, then Saturn, then Uranus and Neptune. Yep.
But what about the three-body problem?
Yeah.
Not the novel.
Yeah. I just got into that conversation with someone yesterday here, actually. The three-body problem in physics, obviously, is when you have three objects orbiting each other, trying to figure out the very complicated orbits. And three-body problem, and we had to solve those, but, honestly, the three-body problem these days is not as daunting as, say, solving the orbits of every star in a globular cluster where you have, say, 1 million stars. They're all gravitationally interacting with each other. Figure that one out. There's no desktop computer that can handle that easily, that equation, that set of equations. But yes, the three-body problem is a fundamental poser that, all of us deal with in astronomy and have to deal with. I'm not sure what your question is about it. Okay, I saved that. That's Albireo. Let's go back to our...
I don't have a problem with it. I just, before computers, it was supposedly impossible to calculate an accurate trajectory, position, whatever, in a three-body situation.
Yeah. In the past, they used slide rules and paper. Lots and lots of paper. Okay. So there's Albireo. Albireo is the actually eyes of the swan, Cygnus the swan. And in effect, if we look at the constellation art, you can see
eyes. It's whatever.
In Stellarium, it looks like an eye, right?
Yeah, it's the head of the swan.
It's the head of the swan, of course, yeah. But now moving back in Cygnus, we move to this beautiful little gem, which I absolutely adore. It's this beautiful little nebula. It's known as a stellar nursery. Okay, and we're gonna head to there next. It's actually called the Tulip, as in the flower, Tulip Nebula. So we're gonna go there now. You'll notice the telescope is sliding a little bit back, and you can see we're zoomed in a little bit. Let's zoom out enough. Okay. All right. And now what I'll do is I'm going to change our gain up to 200 and redo our view here. I'm trying to see where this nebula is here. Daryl, can you take care of who asked Lewis question about? He said, "What's that white stuff on Stellarium?" I'm not sure what he was talking about. Do you know?
I'm not sure either. Can you show Stellarium?
Oh, I see. Okay, yeah. Sorry, that's the swan, Lewis. I was actually showing constellation art, so you were seeing this. All right. Okay. All right, so we're gonna see if we have the Tulip Nebula here. I think it's like right here, but I'm just gonna do a quick 10-second shot, or maybe 12-second shot, just to see if it's there. And if it is, we'll actually do a great exposure of it. And then we're gonna keep moving up Cygnus. Then we're gonna go into Cepheus as the night wears on. We'll be able to see. So yeah, it's right here, I think. Yeah, okay. All right, so what I'll do now is just bring that down. I saw that and I should have. All right, so now we're gonna basically just move north a little bit. Okay. All right. So right now, you'll notice up top, right up here, it says it's searching. Okay, it's actually searching for a guide star. And now it's found it. And so now we start our exposure. This exposure is going to be 25 seconds. Interesting, because to photograph this nebula with a normal telescope, you have to do like 3, 4, 5 minute exposures to get what we're going to get in 25 seconds. Now, that's because our telescope is set up with a system to make it 25 times faster. Gives us a wider field, larger field of view. It's a very nice wide-angle telescope system now. And that's nice. It used to be an f10 telescope, if you know photography. Now it's an f1.8. Hey, Curtis is here. Curtis Horn. There we go. All right, now let me add my stack and take out the previous buffer of beautiful Albireo. Curtis has a physics idea. Do you think a theory should be required? Oh, here it comes. It's coming in. Hang on, Curtis. 1 second. Okay, we're at 200. Let me just set this up, Curtis. Bring this back. Okay, there we go. Look at all that nebula in there. All right, Curtis says, basically, do you think a theory should be required to predict the rest mass of all particles, or just the experimental results from particle experiments? For stable physics, it should clearly give a rest mass we observe. Yeah, that's true. It should give the rest mass. I'll think about that, Curtis. There's a few thoughts I have on that, actually. Maybe we can talk offline about it, because it's one of those concepts that can easily get into weeds, as you know. But thanks for coming tonight, Curtis, and hang out. We're going to be looking at some other things. All right, this is the Tulip Nebula, and let me give us a annotation here. And I'm telling the telescope to tell us what's what. All right, so it looks at that. That's what it knows. It doesn't have an identifier for this. It doesn't have everything, but it's identified the star right near it and tells us the magnitude. Stellar magnitude is how we tell how bright stars are. When you look overhead, like at 9 p.m. tonight, you look up just about overhead, you'll see Vega, the bright star. It's very, very bright. It's magnitude 0. Okay? That doesn't mean it's the brightest. The brightest magnitudes are negative. So we see negative magnitudes, like the moon is minus 12.6 or something like that. The sun's minus 26. Okay? And it's an exponential, so 5 magnitudes 100 times fainter. If it's from 5 magnitude to 10th magnitude, it's 100 times fainter. From first magnitude to hold on. Stoner Tana's with us. Hello there, Tana. 1 stoner, 3 cats. Nice to see you. Okay. I'm going to just take the annotation out, and I'm going to start to try and dig out a few bits of data here. There we go. Look at that, guys. Look how pretty that looks. It's a gorgeous night, Daryl. Look at this. Okay. Wow, that's nice. Let's just do this. We'll fit the width in here. There we are. Wow, that's really pretty. And the longer we go, the more data we get, and that's, in other words, the more data we can see clearly, because we get rid of a lot of the noise. Another thing to notice for what we do, you'll notice these green bars. I have this set to 8.19. What the heck is that? Well, it's called the full width half maximum filter. And if you look at how a star image is defined on a photograph, you'll see it looks like kind of a bell curve. It has not a point, but a rounded top, and it tapers off and then spreads a little bit. That's the stellar shape that you see on the curve. You'll see more of that when we do our spectroscopy for the new telescope. And so when you look at the star's size of that, okay, you want to minimize the size of that peak. You want that to be as small as possible. That indicates that it's more well focused. All right, the smaller that width, the more focused the object, the star is. And ideally, you use the fainter stars in the view, and that's what this system does. It actually looks at all these stars in here, and it gauges the width, and it comes up with a number that makes it as small as possible. And when we actually do that, it looks like this. Okay, these are the sample stars it's using right now. You'll notice that it's not using this bright star. It's using some of these mostly faint stars. Okay, and then it gets the best. It gets the best focus based on those. All right. So that said, let's go back to our stack now. Our stack has not been destroyed. It's just set aside for the moment. Yeah. We're getting some good detail in here tonight, Daryl.
Well.
Wow. Yeah.
Your black line and usually a little farther to the right.
Yep.
Closer to the peak.
Yep. So if you notice these lines here, for those that may or may not remember, a little refresher, we have a red, we have a green, and we have a blue line. RGB values. That's what together they all make a color photograph. You can have a red, a green, or a blue. Okay, and that's using the RGB color palette that we're doing right now. And the average of them is this white line. And so we actually want to make sure that we take our curves and align them up underneath each other. So I color correct. And when I do that, you notice that red curve shifted slightly to the right. And then the average curve changes ever so slightly. This is the black level. And as Daryl pointed out, if the black level is too far, say this way, it gets too washed out. Kind of like you're photographing in a light polluted area. We have no light pollution out there. Very, very little. Okay. Let me resume this. So, in any case, if we move that black level to just the left of the peak, we'll get the maximum darkness. Look at that. Now we can see other details popping out. This is the mid-level. And if we move this toward the black level, we get what's called a push. We're actually over-processing, and it allows us to see details of what's in there that are hiding within all of this. But if we bring it back to where it wants to be, well then it's going to be a little bit further off, and we're going to actually get a better balance of tonality and stuff. However, all of this is stuff that you can do yourself, because we actually, when we save it, as I'll save it now, we have 12 shots taken, and I'm going to change this to Tulip Nebula. Oops, I messed that up. Tulip Nebula. Alright. If I hit save now, it's going to save what's called the astronomical FITS format, F-I-T-S. And that's a flexible image format that allows us to do processing on it. And it's like a raw format. Right? Nothing's done to it. It doesn't even have this done to it. It's actually purely raw. Alright? But then, if we save it exactly as seen, well then, you'll see it just like you see it on the screen. And that shows up as a PNG file that we can ship out. So you get the FITS file and the PNG file, yours to play with and do whatever you like with. Donald Kunzer says there's a straight line of stars left of center.
There's actually at least a couple.
Yeah. Is he talking about this line here?
No, farther to the left. There's a horizontal line.
And this one?
That's the diagonal line.
Okay.
Then the horizontal line is just right. It's up and down. It's right on center, or very close, but left of image center.
Okay. How far from this red star?
About halfway out.
Halfway out to here?
Yeah, and it's right above your pointer.
Yeah, talking about this guy?
Actually, the one just above it, but
This guy.
yeah, and it actually continues farther on to the left.
All right, I see one here.
Yes.
Yeah.
So all that together is the horizontal one, and then there's the diagonal one up above it.
Gotcha.
Closer to center.
I gotcha. Interesting. So let's see. We got 17 shots here. I'm going to drop this down a little bit to. Okay. So we have, if we look at our full width half maximum filter, every shot we're taking falls within the range we need to keep the stars perfectly round. And that's what we got right here. So we zoom in, and you can see details in here, but the stars are round. They're nice. There's a little elongation, which we do have some wind out there, but we're okay for the most part.
Nice detail when you zoom in.
Yeah.
Red area down at the bottom, the dark arms, the dark nebulosity in there.
Right here, yeah.
And kind of a wider, lighter area.
Right here.
Toward the upper right, yes.
Yeah, this is interesting. I mean, it shows a almost three-dimensionality, three-dimensional nature here, you know?
Yes.
Very cool. All right, so we have 20 shots. We'll save this.
It's a nice pick.
It is. Okay, we'll save it here and move on because this will bring us back. We're going to go back to our low light mode from our deep sky mode. And this is our low light mode. We'll back out now. And go right to here. All right, let's go and find the next item. There's another object in here that's really interesting to look at because it really has a real incredible history. And that is this guy. This is known as the Crescent Nebula. And, you know, those of you that come here know that we will photograph some of these objects over and over. But there's a reason we're doing that. Because if something changes, we'll probably be the ones to notice it. And that's a good thing. So here is the crescent. You can just barely see it there. I'm going to bring it down.
Also known as the Ear Nebula, according to Stellarium.
Is that what it said?
Yeah.
Wow, the Ear Nebula.
Well, it looks sort of like an ear.
I guess that's somewhat true. I'm going to bring it down, center it up in our crosshairs here. Okay. All right. Yes, Donald, it does sort of look like an earlobe, doesn't it? Now, it's amazing how, you know, to our eye or to a big telescope like this, you have to take a long photograph, you know, in order to see details. But that's just the way it is. You know, it's pretty interesting. I see, Tana, you have a question. Hold on. I'm just going to do one thing here. I'm going to zoom in. This red square is our field of view. It's 1.5 degrees by 1 degree in size. And we're centered on this guy. So I'm going to center it. And then we're going to synchronize our telescope. So you'll see the STLS move right into the middle. So now we have our more precise targeting available to us. Okay. So back out here, we will get rid of this grid and that one. Then we have that one, which I'll share with you at some point. Okay, we're going to be searching here. Takes about 12-14 seconds to get our guide star. But we can just start going. And if it doesn't work, it doesn't work. See, it's working now. And we'll do 25 seconds. All right.
Gonna leave your gain at 200 tonight?
Yeah, it's on 200 now.
All right. Well, sometimes you run at 250.
I do.
Well, darker the moon. For a while at least.
Yeah. It's trading off with I'm just trading off with the sensitivity of the sensor and stuff. But you're right, I could. Okay, this will be good. Let me come in here and clear the last image. Let's do this. Okay, there's the first image. You'll notice it's kind of noisy, right? Well, when you zoom in, you'll see it. You say, "Ugh, that's no good. It's noisy." Oh, I'm going to refocus, too. I got to do that. But now the second shot, watch. When the second shot comes in, look at that. See? It immediately got sharper. And I'm now going to go back to low light mode for a moment because I'm going to take care of focusing here. All right.
Stoner, I hope I didn't disappoint you. It's just, you know, we're in summertime and Betelgeuse is a wintertime object. If you get up really early in the morning, you can see it over in the east before sunrise.
Yeah.
Actually, when I saw the recent Mars-Jupiter conjunction in Taurus made a very pretty view over the eastern sky with the Orion right under it.
Very
Really
nice.
pretty view. One of those times I wish I had a camera to take a picture.
Well, you should have taken out your Celestron.
I was looking naked eye.
All right, we're focusing now. When stars are defocused, that's a trick we use to actually check out the colors, because sometimes the point sources are hard to see color within, you know.
Stoner was asking about the star of Betelgeuse in Orion.
Oh yeah, for tracking their progress. Thanks, Tana. I didn't.
There's seen some interesting stuff going around lately, though. That Anton Petrov guy and some others have been mentioning it on YouTube. There's some thought that Betelgeuse might be a double star and it's consumed its companion. Like there's a second star actually inside the body of Betelgeuse.
I don't know how that would actually work.
Me neither.
From a physics standpoint. All right, you'll notice this curve that was built here. The lowest point on the curve is the best focus. And at best it was 5.19 and now it's 11.6. You'll notice that now when it's finished and we get the green, it automatically focuses to a point. So now the stars look stunning, and now we can come out, and now the work's done. So we can back out visually, and there's the beautiful Crescent Nebula. And now what we'll do is take that photo again. We'll go 25 seconds again.
Well, Betelgeuse is, I mean, I've seen it described as a red hot vacuum. You know, it's so big but so tenuous. I mean, a star, a binary star, a secondary star, could it be inside the envelope of Betelgeuse, so to speak? You would think that if it had any size, it would be visible on its own.
Well, it depends on a lot of things, but I don't believe that would be something that's actually possible, because if there was a star inside of Betelgeuse, it would be trying to pull in a massive amount of Betelgeuse's mass. And we'd probably notice that, and it would probably leave all kinds of turbulence. Now, Donald Kunzer asks a good question. Is Betelgeuse large enough for another star to graze it? And that's the thing. Maybe there is a star close to it, and if it is grazing it, it might pull off mass as it goes around it, and that could be responsible for some of the large bulbous blisters that we see on the Betelgeuse outer surface, because Betelgeuse is one of the few stars that we can actually resolve to a disk. Other stars are all points of light. Antares is one we can resolve to a disk. Even Alpha Centauri, the closest star system to us, is not big enough for us to see the stars as disks in the sky. Even with our most powerful telescopes, because we just can't see something that small. Okay, example. Take a 25-cent piece, a quarter. How far away from you would you have to move it to make it the same size as Alpha Centauri's stars singularly would appear in the sky? How far away would you have to move it? Okay. The answer is astonishing. It's 750 miles. That's how far you'd have to take an ordinary quarter and move it away from you so that it appeared the same size as Alpha Centauri stars do in real life in the sky. We don't have a telescope that can see that. Antares, though, is much further away, but because it's so much bigger, we can resolve it to a disk. So it depends on that, what I mentioned before, that luminosity class, that Roman numeral. Okay? If that Roman numeral after the spectral class, which is the OBAFGKM, in Antares' case, the M, okay, very red, that spectral class makes it, that luminosity class makes it a very, very large diameter star. And so thus we can actually see, the size of Antares in the sky. It's really astonishing.
Antares actually does have a secondary star. It's sometimes described as green, but that's a contrast effect. It's actually bluish, I think.
Mm-hmm.
It's very close. It is visible under perfect seeing conditions and possibly with an occulting bar, something to block the light of Antares. But I know people have seen it. I have never seen it myself.
Mm-hmm.
It is very close to the primary, but it is visible. But it is notably a double star.
Yeah.
Antares often being considered to be similar to Betelgeuse, another prime supernova candidate too.
Yeah.
And at a roughly similar distance.
I think Antares is a little further. Right? Betelgeuse is between, they say 500 to 700. It's interesting how they can't really get a good distance to Betelgeuse. But 750 is what I heard, of late.
I thought I'd heard the same for Antares, 500 or 600.
Okay. Well, you'll look it up right now and find out. Hi, Judy M. What's happening? Cosmic Ray's here. Ray says they just mapped Polaris. That's cool.
Approximately 550 light years.
All right. Oh, Michael, you're welcome on the analogy. Michael said that he liked the analogy of that's a quarter, 750 miles away, is how big in diameter Alpha Centauri stars would appear in the sky. That's the diameter we're talking, and there's no telescope that can resolve that. So here you see this beautiful object. Let's see if we can zoom out and get an annotation on it for you. All right, look at the clouds of beautiful red nebula around it. Absolutely incredible. Let's color correct here. Yeah, see, the color correction shows the red better because now you actually see the red clouds. All right, so we're gonna throw up the annotation here, and that's the previous one. We're gonna do this now, and there we go.
Antares is actually closer than Betelgeuse. Antares, this is just Wikipedia, so take it with a grain of salt, but says the distance is 642 and a half light years. Betelgeuse.
Yeah. All right, I'll save this image with annotations, so this will be out there as well. Okay, so what that'll do is that'll have this image out there. You'll see this image out there. That's the image that's saved to the server, so you actually have identifiers and all that. And that's just the picture, the pretty picture. But if we save it over here, that's going to save without the annotations anyway. So we can sit here. We've done 15 so far. We'll save. And so now you see up there, the FITS file went out there, and now we'll save exactly as seen. And then the ping file, the one that looks just like you see it, is now out there. And that's cool. All right.
Dean, we're no longer on the Tulip. We haven't been for a while. This is the Crescent. If you're still seeing the Tulip, you may want to check on your YouTube and see if your live is red or not.
Okay.
The little red dot is lit up.
Yeah, Dean Bustador is with us. Thank you, Dean.
And the red clouds are all hydrogen, red glow of hydrogen nebulosity in the constellation of Cygnus in that area of the sky.
Yeah. Now, I started to say, this beautiful nebula is a star blowing a cosmic bubble. Oh, he's right. He's seeing it here. He's seeing that. Because I haven't changed it yet. I'll do that right now.
Okay.
There you go, Dean. Thank you for noting that. Because I have to make that correction. I forgot to change the name. Dean is exactly right.
Senior moment.
So the Crescent Nebula is a star blowing bubbles, and it's this star right here. Okay, what's going on in the Crescent is phenomenally interesting, and I'll tell you why. Because this star right here is a star that is known as a Wolf-Rayet star. They're 40,000 Kelvin, which is literally, very, very hot. Maybe this is the surface now. The interior is even hotter by hundreds of millions of degrees. But what happens is the star itself, for some reason, it ejects its outer layers. Because in a star, the only thing that's doing the nuclear fusion is the very core, right? Then you have that big outer part of the star called the envelope, and that's just along for the ride. You're not doing fusion in there. That's just hot plasma, and plasma is just protons and electrons. The electrons are stripped off the atoms, and all you have are the nuclei running around in there, and that's what we have. And so the hot plasma is, in the Wolf-Rayet star's case, is also creating these massive stellar winds from the core, pushing out. And by pushing out, what happens is they actually defeat the gravitational force trying to collapse the star, and thus holding it in equilibrium. Okay? So we see that with a lot of stars, right? All stars, they're at what's called hydrostatic equilibrium. The force of the radiation outward is equal to the force trying to pull them in, the gravitational force trying to pull them in. And so stars are stable. All right? But in this case, gravity is losing to the very, very powerful stellar wind pushing out from the core of these Wolf-Rayet stars. And look what it's done. It's pushed those outer areas, the parts along for the ride, it's pushed them out here. And so we see all this gas that is excited by that star being so hot. The ultraviolet energy being given off is exciting and causing the gas out here to glow. And the shape is you would think that it might be spherical, right? Right? Because that's what you would think. If it's just pushing stuff out equally on all sides, it should be a sphere. Trouble is, the interstellar medium is full of stuff, full of dust, full of other areas of density, like this dark nebula that you see right here. Okay, that's a dark nebula right here. Okay, and that stuff is impacted by this expanding gas and slows it down. On this side, it's less impeded than this side, where it's actually been slowed down tremendously, and it's hitting denser materials. So as it blows outward, some parts keep going and other parts are slowed down. So we get odd shapes to some of these stellar bubbles that we see.
And the star being a Wolf-Rayet star, it's a prime candidate for a supernova down the road.
As a matter of fact, Wolf-Rayet stars are usually in their end stage of life at this point, if you call it that. And that pretty much tells you what we're trying to do here. We're trying to show stars' life cycle. This one is at the end of its life, and it could go supernova while we're alive, or it might take 100,000 years or 100 years. Either way, we live in such a narrow window in the universe that to see the things we see when we see them is actually pretty impressive.
Mark, could you excuse me a moment, please?
Sure, go ahead.
Be right back.
Okay, so... Oh, Daryl must be running his fan because you hear that noise now is gone. Hey, the Goblin's with us. Nice to see you, man. Good evening. Very nice. Very nice. Okay, so as we get down here, let me show you our all-sky camera right now. This is the view of the all-sky. All right, here is the Milky Way. Here, there's a little satellite going through. So we see this beautiful view, and we can see constellations by just, oops, not that, sorry. Hit the wrong button. So here's our constellations up here. You can see Vega and the constellation Lyra. We have Deneb and Cygnus right here. And we have a way to do this. So I just wanted to check it, and it looks like we're nice and clear as I expected. There have been fires out there which have been responsible for clouding up the sky a little bit. But no problem. Mr. Django, Steven, how you doing, man? He's over in Belgium. His day is already started. My night's coming to an end, right? Okay, 32 images here. We're gonna save this. Save it exactly as seen. Okay, Steven, Mr. Django says, last day of work, and he's going to be retired. All right, brother. Well done. Well done. Izabela says, wow, you're free. Well, congratulations. Congratulations, buddy. I'm glad that you have retired. And you know what that means? People here are going to have to visit Django's backyard. It's just a site that I should give you a wrench. I haven't yet. I'm sorry. So you can put up links. I'd like to put up a link to your site so people can go there and check you out, Mr. Django. Steven Smith does a lot of cool work in astronomy, and I think it's kind of cool if he gets to show it off to you guys. All right, we're going to zoom in a little bit here.
Doodah.
Hey, welcome back.
Thank you.
All right. So yeah, this is good. Okay, it's just a gorgeous night. I mean, look at the detail in here. And I'm actually going to enhance the detail here. Watch this. Okay, now watch the detail. Bam! Look at that. All that detail is now showing even better. That's incredible. Looks really nice. One of the nicest crescents we've ever done. Okay, we'll save this at 36. Save it exactly as seen. Back out to show the whole thing. And remember, we have our annotation for it as well. And that's up there too. Okay. All right. Well, I hope you guys enjoyed the Crescent Nebula. It's a star that's on the brink of extinction. It's going to probably explode in a supernova. Man, that'd be so cool to see a supernova from this. Something we're used to seeing. That'd be outstanding. Okay. Zoom in a little bit. Okay, now let's come out and let's move forward a little more. And let's go. I do want to look at the Gamma Cygni Nebula.
It's a great big square nebula.
Yeah, he's not. He's kidding. All right, so what we'll do actually.
You show it right there. It's square.
I know.
Or is it cubical?
Yeah, it's.
They're just highlighting that area, folks. I kid.
Yeah, Stellarium doesn't show the whole extent.
Yeah, there is a lot to see there. That's why it's highlighted.
Yeah.
But that's all. Red nebulosity is what he was asking earlier.
Yeah. I'm going to come here, though. We're not going to look at this. We're going to look here. Because this has some other interesting nebulous detail in it, too. We've got blue reflection nebula mixed in with diffuse hydrogen nebula. And so we're going to go there and check those out.
There should be a square nebula.
Hey, no. No such thing.
Actually, there's some planetary that...
Oh, yeah, as far as the shape, yeah, but not by the name, yeah.
Looks quite square, I forget.
Yes, you're right.
Hubble image or something.
Okay, let's okay, there it is. So we're gonna bring that over. All right. Okay. We're gonna try right here. And I'm going to go down a little bit. I have a hunch. My hunch could be wrong. But I'm going to try it. Alright, we're going to do another 25-second shot here. Alright, and we'll go into low light mode here. Go out of low light mode and go into deep sky mode. Okay. So there's our last shot that we did of the beautiful Crescent Nebula. And we'll clear that. That's up on the server. And you can go download that very image and enjoy it. Put it on your desktops and everything. Let's see here. Oh yeah, there they are. That's what I wanted to do. They were a little... hunch is right, but it's just a little off. I gotta move it. I will move it back. Just a minute. I wanted to show that nebula and get the blue stars in there. And I got them, but I want to make sure that they were more centered, that's all. You can see the nebula here. What did you get fed up and quit about? Oh, retirement. Okay.
Working for a living.
Okay. All right, so this will be good.
So Django retired, and
Yep.
everybody started talking about retirement.
Mm-hmm. I'm not a retirement kind of guy. I think I just move on to the next, thing to do. All right, let's do this here. Let's clear this. And that'll be moved over here now. This photo illustrates the beautiful colors of the universe. And when it comes in, you'll see it here. Okay, you have this beautiful blue. This is called a reflection nebula. And it's not a reflection, really. It's actually what's called scattering. And see, because in here, this is all dark dust in here. And the dust has a property where the dust particles are so small that they love to scatter the blue light from stars that hits them. Now, stars show up with all manner of colors, right? Red, orange, yellow, green, blue, and violet. So the blue light's high frequency, high energy, and these little dust particles love that. And so what they do is they take in the blue light and then shoot it back out in all directions. So it's scattered everywhere. And so we see a blue nebula within these dust clouds. So when we see some bright enough stars. And then the red is the hydrogen emission, where the hydrogen in these clouds is neutral hydrogen atoms. The electrons are bounced off by ultraviolet radiation from stars within the nebulae. And when they recombine with the atom, they actually give off light, and that light is this characteristic red color that we see. So I'll take this down here for a minute, and I'm going to actually move this over. Okay, and so now what we can do is bring this up large scale and check it out. Look at that.
What do you think is doing the ionizing in that image?
There's probably a number of stars in the region that are full of ultraviolet energy, and they could be buried in these dark clouds. I don't know. I don't know if any papers have been or studies have been done to show.
Well, I know in the case of North America and the Pelican, yes, the stars doing the illumination and ionization are hidden from our view by dark nebulosity in the way.
Yeah. Okay, this is. Let's see if the annotation knows what this is. Oops, that's the wrong thing. Sorry. I want the annotation. Let's find out. Let's create a. Oh yeah, so it knows what the reflection nebula is. You see how quick it is? It just automatically knows now. I like that. That's because we're sticking in the area we're still in. All right, so there's our labels. It's NGC 6914, right? And that's a reflection nebula. We'll save that, with the annotation. So now that's out there. And then I'll change the name here to NGC. Come on. NGC 6914. And it's a reflection nebula. Come on. Let me just save it. Now, if you want to know where to go to get these images, well, that's easy. It's right here, skytourlive.org. Just head to skytourlive.org, and you will be able to find all of our images up there. There's a location. When you scroll down, it'll say, take me to get cool images, and you'll go and into the directories. That's one way. The other way, and I'm patiently trying to wait for the folks that are helping to get our app published to get back to me, and we're trying to get our app for the iPhone and for the Android devices and the Mac and the PC out there, so people can start using our app to look at all these beautiful images and just scroll through them and have fun. And it's a beautiful app written by none other than Izabela Melamed here in our chat. And Izabela, as I said, that's why I call her a superstar. And she has this beautiful app she wrote that helps everyone sift through and look at all the things that we've done. You could look at every photo, for instance, we've ever taken of this, okay, if you wanted to, and search for it and see them all together. You can look for differences between one frame and another and see if there's an asteroid in one frame versus another. That's actually real astronomical work that people do. And so I think that's kind of cool. But that's our Izabela. She's just amazing that way. Yeah, she's a masterpiece, all right. Yeah, notice there's two reflection nebulae here, but there's another one right here. You see that? And what I'll do is I'm going to push this and see what else is there. All right.
That's nice.
So you see there's a lot more there. And if we... I don't want to see that we're at the peak, and I don't want to come any closer because that'll ruin this. So I'm going to take this back just a bit. There we go. And I'll do a color correction, see if we get a better rendering of the red. And we did. Oh, that's really nice. Look at that. This is why I wanted to do this one. Izabela, you're welcome. Izabela said thank you. For what? Oh my gosh. We should be thanking you every night, and, well, I think it's important. All right, Steven. Have a good night. That's Mr. Django. And actually, you're actually moving into your day, so have a good day, brother. And congratulations. And don't overdo it, okay? Because you gotta make sure you stick around. Vince Giglio's with us. He says Cherenkov radiation is given off by particles traveling faster than the speed of light. Okay, in a medium, there are telescopes that look at the top of the... I'm trying to read what you said. In any medium, there are telescopes that look for it at the top of the atmosphere. I'm not sure what you're saying there, Vince.
Donald had asked if the glow was
here.
Just in general, I guess. He says, "Is that similar to the glow in nuclear reactors?" And I answered to him that that's called Cherenkov radiation, and it's given off in nuclear reactors in particular. That blue glow is it's protons and electrons traveling faster than the speed of light in the water, and the causes the water to give off light. And then Mr. Vincent Giglio,
yeah, was
saying that Cherenkov radiation is given off by particles traveling faster than the speed of light in any medium. We don't dispute that. I was talking about nuclear reactors.
And water in particular.
Yes.
Okay. All right, let's see what we got for... I'll bring this back up, and we'll leave it full screen, but we'll just bring this back up here. I'll dock this back up, so we're docked again. And then I'll just shrink it down a little bit so we catch a little more of it. Look at that. Wow. Okay. I will save that.
I was going to say something about that white glow off the left edge. I know we've talked about that before.
Yeah, that's amplifier glow from the camera. Unfortunately. We process that out when we do the processing. So you see that this is these beautiful knots of nebulous detail. I wanted to capture this segment of it. And we're going to stop right here with this exposure. Okay. And now I'm going to go into our low light mode again. And let me do low light mode. Okay, and then do this. All right, and we'll let's bring back the telescope for a minute. There we are, and let's notice that there was the movement of the stars there. We're getting some wind, so I'm just gonna go down here. Catch the top of this. All right, let's do 25 seconds here. And we'll go into deep sky mode. Yeah, it's beautiful. So now this will be down lower. All right. We'll clear this. And while that's coming in, I'm going to go look in the constellation of Cepheus up here. And see, because we're right there. I want to go up here. Find out how far away. I think we're up here. Okay, right there. And all right, so that should be Polaris right there. And it is. So it's high enough.
You can always tell Cepheus.
Yeah.
It's shaped like a kid's drawing of a house.
Yeah, right.
And the roof is pointing down right now.
Yeah, but this is actually King Cepheus.
Yes. Cepheus was the husband of Cassiopeia the queen and the father of Andromeda.
Yep.
But that's a whole other story.
It is. Amanda used to like that. She used to like your discussions of all that.
Yeah.
So let's center up on our nebula now again.
You ever seen the movie Clash of the Titans? That's the story.
Yeah. So what we've done is we have moved a little bit, and we're taking another photograph of the upper part of this area. And this is just so extensive that, you know, it goes on and on. Trust me. So there's our stars, and I want to capture just this part here. And we'll come back to do more of this at another point. I won't make you sit through the long mosaics I did of this whole area. That's all night long. All we do is take picture after picture of side by sides, and just like each adjoining frame, and I just kept doing it. And we captured the entire Gamma Cygni Nebula, which is that whole square that you saw in there that Daryl was talking about. And with this, we're going to just go to 10 exposures. And then we're going to move up and look at the object that's next here, which is right near Deneb. And this will be another quick grab. Because we mentioned it. I want to show you what we're talking about. This is the North America and Pelican Nebula. Now, you don't see the North America, except it's upside down right here. Here is Mexico. Here's the Gulf of Mexico. Here's Florida. Here's the United States. That's why it's called the North America Nebula. Okay? For that reason. And we're going to photograph the a region of the North America Nebula that's really interesting. It's called the Wall. So what I'll do now is save this here. I'm not changing the name because it's all part of the same object. Okay, save exactly as seen. There we go. Alright, so now we'll come out of here, go into our low light mode again. Alright, and there's low light mode. Good. So now we're going to come back here.
Izabela, probably just because
And then
he was one of the characters in the story.
okay. Let's do
Cassiopeia was the one that actually caused all the problem in the first place.
I know, what's wrong with that lady? Okay. We'll do this area. I'm just going to go to that area. Hey, Fantasy, what's up? Nice to see you. Telescope moving farther toward the north.
Cat got your tongue, Mark?
What are you talking about? I've been talking. Haven't you been hearing me?
Whoops.
I've been talking. Haven't you been hearing me? All right.
Hello?
Yeah, I hear you. Daryl's having troubles.
My microphone is unplugging itself.
Well, not your microphone, your speakers, because you weren't hearing me.
Well, my, my headphone.
Okay.
Headphones.
All right, let's do a quick shot here just to see if I'm where I want to be. Yeah, I've been talking the whole time, but your headphones got unplugged, so you didn't know.
Yeah.
All right.
Oh, the headphone jack on this microphone is on the very bottom, and it seems to be developing a habit of unplugging.
Well, you know what they say. Duct tape. There we go.
I hate duct tape.
Okay.
I was an industrial mechanic for 40 years, okay? Duct tape is not the answer. Duct tape is never the answer.
It's the answer to everything, remember?
Eh.
All right, we're going to move a little bit now to the west. This was actually a good placement.
Actually, one place that came in handy, I remember reading about this guy a few years ago. A bush pilot up in Alaska had parked his airplane, and grizzly bear came by and ripped the body of the plane apart because he had stashed salmon inside the cargo space of the airplane.
Yeah.
And it was one of the old-fashioned planes that had a fabric skin, you know.
Yeah.
So he got a whole bunch of duct tape and he taped up the fuselage and flew it out of there.
Wow. I remember being on a plane flying to Roswell, New Mexico. And the plane had what looked like duct tape holding the wings together. It was actually called speed tape. But it looked just like duct tape on the wings of the plane.
Yeah.
And it was really funny to see it. I made a comical post about it.
They used to call it 100-mile-an-hour tape.
That's right, because
they used to use it in NASCAR or in stock car racing.
Yeah, that's right. Okay, guys, this next object is going to show up after this guy. I'm going to clear him because we got him up there. This is the North American Nebula, and it's part of the region of nebula called the Wall. A lot going on in here and a lot to unpack once it starts showing up. But you're going to like it. There it is. And we have a lot going on. Like I said, this is a beautiful red diffuse nebula in here. This is all dark nebula in here. You see the dark dust. It's sitting in front of a lot of this stuff you see here. A lot of this other stuff it's sitting in front of it. And this is hydrogen gas. Whoa. This is hydrogen gas that's glowing. And hydrogen gas that's glowing, it can easily be overwhelmed by dark dust. And so where the dust is dense, you won't see the hydrogen glowing as brightly at all. I'm going to color correct now, and you'll see the color change slightly here. There we go. Yeah, but look at that. See this dark dust up here? Look at all that. Beautiful tendrils. This is just a stunning area. You know? Okay. Very nice. So let's zoom out to see the whole image. This is the whole image of what we're looking at right now.
This is what I was saying earlier. The dark cloud you see right as center, there are bright stars behind that cloud that we can't see that are illuminating North America and the Pelican, which is out of frame to the right, upper right.
Yep. This is really pretty. Let's do this, and let's also get rid of this and bring this full screen so people can get a nice view of this. Look at that. That's really something. That's really something. Yeah, so the thing about it is, in the universe started with hydrogen, and mostly hydrogen during the Big Bang, a little lithium, some helium. And what ended up happening was the hydrogen, of course, went into making stars. The stars evolved, became red giants. Some went supernova. Some just created and died a slower, more gentle death, like our sun will. And they made planetary nebulae. But in their outer regions, they had molecules. Because the like Antares and Betelgeuse, it's so big, there's molecules in that outer star's atmosphere. And then that sloughs off, and Betelgeuse is also blowing bubbles, by the way. It's blowing giant bubbles of material that leave the star because it's so big that they're not gravitationally bound with the slightest pressure and disturbance from inside. So what ends up happening is, where did we go here? Oh, okay, sorry. when you muted, the music stopped, and I thought something happened to the stream. It wasn't. It was just the music quit. It stopped and went to the next cut at that point. So,
you trying to say it was my fault?
No, I didn't know what it was. I thought I lost the stream, but I did not. Okay. So, what happens is, when you look at Betelgeuse, okay, it makes molecules in that outer atmosphere. And sometimes it makes carbon molecules. It makes molecules of other material that it was made with. And basically it makes a slurry from which, once it's liberated from the star, can go into a dark nebula like this. Everything you're seeing here, all this dark nebula, that was once in the outer atmosphere of a star or created during a supernova explosion, or a nova, or a planetary nebula. And so the universe is littered with this dark debris. And as I've said, life began in the dark. Okay, you might have heard one of our SkyTour songs that we composed, and it basically says life began in the dark. This is exactly the type of place where life could eventually begin, because this dark dust is going to clump. And when it clumps, it might have enough hydrogen to make a star. And if it makes a star, then that dark dust could then start orbiting the star like it typically does, make an accretion disk, a disk, like our solar system plane. And then it could end up going into forming clumps within that and making planets. And it's within this dark dust that all that material to make planets is found. This is just the coolest thing.
As Carl Sagan once said, we are made of star stuff.
Exactly. Every atom in your body was once made at millions upon millions of degrees in the heart of a star. And it's been liberated through supernovae. In part, I mean, even stars that die a gentle death like the sun, they can create, more massive atoms in another process called the S process, or the slow process, otherwise known as neutron capture process, and beta decay. So there's a process that takes place in stars like the sun, and it takes a long, long time for atoms to be made that way. Okay. However, if you look at the a supernova, you find that more massive stars can create much more massive atoms within their cores. In fact, all the way to iron, which I mentioned before, which is number 26 in the periodic table. So if you can get to iron, beyond iron, stars cannot make elements beyond iron. They just can't. All right, and the reason has to do with the energy required to make iron versus the energy given off from hydrogen fusion. We don't see fusion happening beyond iron because it would actually be a negative energy gain process. You know?
Your stars appear
I noticed that.
Trailing badly.
Yeah, I'm not sure why that happened. Let's go check the...
Well, they used to say that elements heavier than iron were created during the forces of the supernova. And nowadays, I know that's changed somewhat, that they like to say the heavy elements are created by exotic things like neutron star collisions and stuff like that.
Okay, I see what happened here. I must have clicked off the full width half maximum filter. Well, we'll come back and do this another time. We're getting some wind, which is causing this problem. But that's okay. We'll still save it anyway, just to have it for the record. And then we will move to the next object. I must have clicked that by accident, and it turned off our filter. So you see our dashed lines here were where it was supposed to stop taking pictures if they went out of bounds, and you can see that quite a number of them did. All right, but as I promised, we will save it anyway, and then we will we'll save it exactly as seen. But you got to see this dark nebula here. This is fascinating. It's really important stuff. Again, life began in the dark. And that's where it all happened. Dark nebulae are my hot button. All right. So, that said, let's gesture in that side of the screen again. And now we can now go to this next object here. Let's back out a bit. Well, we got the cocoon, we got the elephant's trunk. I'm going to do the elephant's trunk. I haven't done that in a long time. And not with this camera. This will be the first time this camera has done the elephant's trunk. See the telescope bending way over. Those stars look familiar. Yeah. All right. So let me just pop that up to 300 for a minute and redo this. I see our elephant's trunk right here. Okay, I gotta move a little bit to the west. Alrighty. This is nice. This will be nice. Okay, let me drop this down a little.
You've got moonrise in about
I know, I'm fighting. That's why I'm rushing past the
40 minutes.
Yeah, that's why I'm rushing past the North American Nebula right now. We got wind. Look at that. That's happening because of the wind right now. Yeah. Might take longer to get this image, but we'll try it. We'll do a... Yes, Izabela. The stars are... Look at that. That's what's happening, right? You see there? If you look at the telescope, that's a gigantic sail. You know, that big barrel is a big sail. So it's kind of hard. But we get moments of clarity, so I think we can do a 25-second shot and capture some of these images. So we're gonna go in. Yeah, Herschel's garnet star is in this region. Yeah. So let's do the live stack. Clear the last one. Yeah, we'll clear that. And I'll leave it on the full width half maximum page here, because let's make sure we get yeah, see, too much wind. That would have been an elongated image. We might have to wait for a calmer night, because we're looking at 10 to 11 mile an hour winds out there right now. I just want to get one to show folks what's going on. Could raise the limit a little bit. I don't want to, but I could. I'll go to 8.68 or 8.58. Yeah, it's just right on the border. It's coming down. This next one should be green. Again, this is the elephant's trunk if it comes in. Yeah, okay. Well, just so that I can show you, I'm going to bring it up much higher. It'll be... stars will not be perfect, but I want you to just see it. Alright, so let's see what this next one is. There's a green one. Yeah, see, they're not perfect, but here's the elephant's trunk right here. Move this over. So you can see this nebula right here. And it's going to look a lot different once I clear it up and do this. Jeez. It probably won't get any more than that. So this will be a wasted effort right now because the wind's picked up out there. But that's okay. And we did a great number of objects tonight. It was actually pretty cool. Hey, Bullwinkle, what's up? Bullwinkle 000. From Frostbite Falls. All right, brother. Welcome. All right. So right now, I don't think this is going to help us much.
You might try, I mean, your scope's pointing up high in the sky. You might have better luck pointing to southern objects.
Maybe.
Just a thought.
Yeah. So let's see if we can... Let's see if we can go get one more shot of something in the Milky Way. We could try the Eagle again. What do you think of that?
It's all right.
But then again, I know what I'll do. I got an idea. We're gonna go here. Let's see if we can grab this.
One of my favorites.
Yeah. All right. So this one's, as you can see, that's what it's going to look like once we get it. I just had to see what this camera would do, and I can see that this camera is going to do a phenomenal job with this once we actually can get some more images of it. Oh, look, we got some. But they're still blurry because I got that set too high. It should be down below, below the 7.95 is good. But tell you what, I'm not saving it because it won't work. It's not good enough. We'll get it though another night. All right, so let's go low light. Let's go now. Let's go fit the width in here. All right, and now we'll go back to this. And we're going to swing the telescope all the way around to the other end of the sky. So watch the telescope now. There it goes. All the way to the other end of the sky. It's coming right for us. There it is. You got your fan going, huh?
No.
Why do I hear it? What am I hearing? Wow, this is beautiful.
I don't know.
Yeah, I'm hearing a lot of ambient sound there for some reason. It might be your computer. All right. And then I'm going to take us eastward.
I don't hear anything.
Yeah, they busted door. Whee! That's right. This is a beautiful globular cluster. This is called Measure 22. As Daryl said, it's one of his favorites. And Measure 22 is a cluster down just off the teapot of Sagittarius. And, oh gosh, it's got probably several 100,000 stars in it. Hey, Fairy May, how are you? All right. And it looks like it's a pretty good steady image. Let me zoom in. You know, there's a thing with telescopes. When you move them around the sky, you get a thing happening called mirror flop. You notice how the stars are not quite in focus anymore? That's because of the fact that the mirror actually moves an imperceptible amount when the telescope has been moved from the vertical. So what we'll do now is just go quickly do another alignment. It's using the full field, not just this. Okay. But I want to make sure we get the beautiful, crisp, beautiful gems that these are. So we're going to build that parabolic curve at the bottom again. And the bottom of the curve will be somewhere that the line at the bottom will not correspond to these places where stars were sampled from, like here and here and here. It's going to correspond to whatever's lowest on the fitted curve. The more points we put in, the better the focus. I have 12 because I'm using 12 for just to make it quicker. I should be using like 24 and let it take 10 minutes to focus properly, but I'm not going to do that because you guys want to see stuff. I want to say hello to Roxanne, who is out there listening but not in the chat. She's she's actually new. She subscribed today. So everybody say hello to Roxanne.
Hello, Roxanne. Roxanne.
Yes. I'm sure she's never heard that before. Okay, we got our focus. Notice that's the bottom. And so we're going to focus to that. And that's going to give us our best focus. So it's going to come do the focus run. It's going to center up. And now our telescope is really highly focused. And now if we zoom in, you'll notice that those stars are actually, once we get the wind to stop. All right, let's do this. Yeah, we got to get the wind to stop. Obviously, the wind is affecting this too, guys.
Well, I tried.
No, it's all right. We're going to give it a shot. Cindy Murphy's with us. Cindy Murphy, how's it going? Izabela says, hi, Cindy. Hi, Fantasy. Hi, Roxanne. Excellent. All right, so let's do a 20-second shot of this. Slightly shorter. Might be a little easier. We don't need as long a window of no wind. We're actually, I'm cheating a little bit. We're using, oh, look at that. It's going to be beautiful when we get some nice deep photos of it. I'm cheating a little bit. I'm using I'm allowing the telescope to run on a windy night. Look at that. Wow. That's pretty. Let's color correct because we got some nebulae and areas around here which are kind of cool. I'm going to see what my full width half maximum is set to. Oh, good. Yeah, this is going to work. Nice. 7.95, Daryl. That's where we're at. And so what I'm going to do is... there we go. That's a good rendition. And then I got to... You'll see these dark streaks already here. The dark nebula all around this.
Messier 22 was higher up in the sky. It would rival Messier 13, the Great Globular and Hercules.
Easily.
This is way down in the southern sky from our point of view.
Yeah, and if we zoom in, you'll see that we can resolve stars all the way to the center. And that's really nice. Now I can make it even easier by doing that. Okay. I've mentioned this before, but globular clusters like this are actually called halo objects. They orbit the whole galaxy as a whole, but they do plunge through the disk down and come up into the disk from the other side as well. So they will actually potentially drop stars off on the way through or pick stars up on the way out. It's actually pretty interesting. And this particular globular is only 10,000 light years away. I say only. So you're seeing it as it was 10,000 years ago. And so this particular globular being that far away means, and it's toward the center of our galaxy, means it's plunging through a fairly thick part of our disk. The nuclear bulge is actually growing a little bit just beyond this. So it's starting to grow. So we're actually seeing this plunge through a fairly thick and meaty part of our galaxy.
Yep.
So it could very well be dropping off stars, leaving them behind, and picking some up as it goes through. Kind of like the great mixing, you know? Izabela says that triangle of stars below the globular cluster, the stars in the same plane, or is that an optical illusion? I guess you can see a triangle almost anywhere you look. Where are you looking, Izabela? Triangle of stars below the globular cluster.
One pretty big triangle pops out at me, roughly the same size as the cluster. Just below it, there's that line of stars to the left of your pointer. Pretty bright ones. It's a equilateral triangle. Yeah, that lowest star there on the left is one vertex. Then another line going to the lower right.
To here. To this.
Maybe not quite that far.
Maybe here.
A little farther.
Okay, but.
And right there.
And then up.
Yeah.
I can see that. Yeah, I can see that.
Probably just happenstance, Izabela. I mean, they're foreground objects, much closer than the globular cluster is. That's probably just a chance, alignment.
I agree with that. Most likely a chance alignment. Isn't this beautiful, guys? It's a gorgeous
Every
cluster.
globular is different.
Yeah.
Every one has its own appeal to it.
Yeah. Let's see if there's anything hiding in here. We're going to punch it up momentarily here. Look at that. There's a dark streak right here. There's some streaks right here. There's a streak right there. This is all dark dust. Dark dust lanes down here. There's a lot more down here. So this region has a lot of that dust. Okay. Beautiful. Oh, Izabela, as far as how much it's moved in 10,000 years, I have to get what's called the proper motion of this cluster. Proper motion, guys, is the movement of a star, for instance, each year in the sky. And it's usually measured in arc seconds for some stars. In some cases, arc minutes, because the stars are really close to us and move pretty rapidly. Barnard's star comes to mind. That's one that's a red star that's very close to us, I think 6 light years away. And it is actually moving fairly fast. We've seen the differences in just 3 or 4 months in SkyTour. And so we can actually see the differences. I believe, let me actually change the name here while I'm thinking. I believe that this is Measure 22. It's a globular cluster. All right. So I believe that when you look at that movement of a globular cluster, they're a lot further away. So in 10,000 years, they probably haven't moved all that much. 100,000 years, yes, you'd see motion. Keep in mind that there are many, many light years across, too. So it takes a long time for motion to be perceived from something that distant. We also have to know which way it's going, by the way. Not just the speed it's moving, but is it going up? Is it going down? Is it going left, right? Most likely it's going to be going at some angle to what we see. We don't know. One thing we do know is it's probably not heading away from us, and it's probably not coming toward us.
Stellarium might say its diameter, I don't know offhand, but maybe on the order of 100 to 150 light years.
Yeah, maybe. Let's see. It gives the diameter in terms of the arc minutes and stuff like that. It's like a size parameter. It says, or degrees I see here. 0.32 degrees. Is that what that says? Oh, come on. Let's see here. I don't know.
32 minutes?
Yeah. That's what
So that's about the size of the moon in the sky, about a half a degree.
Yeah.
What that would work out to at 10,000 light years distance, I have no idea.
Yeah.
Izabela says, then how do they know the globulars are orbiting the galaxies? Who was it? Harlow Shapley that discovered the relationship of globulars to the Milky Way?
Yeah.
That was back like 1915, if I remember correctly. This astronomer, Harlow Shapley, I think, he studied, he did a survey of the sky, sort of a statistical survey, and he found that they were centered around the center of the galaxy, Sagittarius, and uh, figured out they were sort of orbiting the galaxy. Not necessarily in the galactic plane, though. I mean, they're, as Mark said, it's a halo object. They're in a big fuzzball around the galaxy, all around it, but statistically, the most are towards Sagittarius.
One of the things they did was they did a statistical study of the size and diameters, and based on their locations in the sky and distances that they could calculate, they showed up as objects, many of them outside the galaxy proper. And so that led to the thought that maybe there are halo objects. Now, why are they such tight clusters of stars? Well, that's something that's never been addressed until recently. Because when you think about it, how in the world could such a cluster form? One way it could form is if it has a black hole in the middle, a supermassive black hole, kind of like galaxies have. So it's possible, and that's sort of a ongoing study right now to see if maybe these globular clusters have black holes within them, and that's why they exist. They could have been black holes created when the universe was created, and most likely it was. And the reason is because of the fact that these stars are what are called population 2 stars. They're very, very old. In fact, when we look at these stars and we look at their spectra, which is something we'll be looking at with our telescope, the next telescope, the spectra shows something interesting. It shows mostly hydrogen and helium and very little other elements in that envelope of the star. Remember I told you that the only part of the star doing fusion is the part in the core, and everything else is along for the ride. Well, that everything else along for the ride was stuff that was actually made with the star. So our sun has tons of, it has phosphorus, magnesium, calcium lines, and hydrogen and helium, all right, all stuff in its envelope that it could never make because it's not hot enough in the core to make those elements in our periodic table. However, it was made with them, and we see that composition when we study the spectra of the sun. When we look at the spectrum of these guys, we see just hydrogen and helium predominantly. All right, and the reason is because of the fact that they are so old that these stars were formed before there were actually many stars that had reached maturity and supernovaed and left all this dust for them and gas and new elements that they could use to make themselves. They were made from some of the earliest gas in the universe. And so the black holes that are possibly in the core of these things could very well be black holes that were made when the Big Bang occurred. So in other words, we could be looking at primordial black holes inside of here, made when the universe was first formed. And it would stand to reason, if this is one of the oldest things in the universe, then if it's got a black hole in the middle, then it's also got to be one of the oldest things in the universe. And it can't be from a massive star because of the fact that it would have to have had time to have many such black holes made and then coalesce into a super merger of black holes to make a supermassive black hole big enough to hold these stars all together. There, we got past that. We took 17 images with 20 rejects. Okay, we'll save it anyway. Okay, we don't want to lose that because that's beautiful. Nice.
I always thought it was interesting that, they call them population 2 stars, but they're the oldest stars.
Yeah.
You'd think they would call them population 1.
I know.
But it's the other way around.
Yep. You know astronomers, they love to confuse you. Alright, so let me just do a little synchronization here.
I would wonder if the Webb telescope, like so much else in cosmology nowadays, may affect the line of reasoning behind globular clusters.
Yeah.
I think it's indisputable that they're some of the oldest things in the universe because of the lack of metallicity.
Yeah. That is. Any other elements other than hydrogen and helium, we call those metals. They're not metals technically, but anything other than hydrogen and helium in astronomy is called a metal.
And some say that the galaxies formed from globular clusters. That may not be the case anymore either.
Yeah, I mean, if globular clusters have supermassive black holes in the middle, you could understand why that's possible. But on the scale of a galaxy, the black holes in the middle of a globular cluster are much smaller than the black holes in the center of galaxies. Much smaller. Less mass. So they'd have to merge to make, because there's tens and tens of globular clusters around our galaxy, and Messier 33, Messier 31, the Andromeda Galaxy and Triangulum in reverse. So yeah, so there's a lot going on there.
Got to start somewhere.
Yeah, they'd have to merge, and the timing to merge is something that's a problem. In other words, we'd see way more black holes in the universe if there was just trillions of these black holes made. We would have actually seen evidence of trillions. We see evidence of hundreds of globular clusters in some galaxies. We don't see thousands. We don't see millions. So it's likely. Go ahead.
If I remember correctly, M31 Andromeda Galaxy has like 1,000 globulars.
Well, it's also got 1 trillion stars. It's way bigger than ours. So it scales up, yeah.
Does anybody else see a dagger sticking into the top of the globular?
Yeah, right here.
Yes, the dark streak you mentioned. Looks like a dagger plunged into the heart of the globular.
I know exactly what you're talking about. I looked at it and saw it immediately. This is your dagger. That's interesting. Okay, we'll save this and be done with this. Okay, let's go back to our low light version. That's interesting right there. And take us up a notch to here. Back out. Fascinating, Mr. Goblin. All right. Let's just do this. We have so many objects here. I want to try to find something that we have not looked at. We looked at that. How about over here? We've looked at that before. It's probably too windy to go too far up in the Milky Way tonight. But we could. Yeah, we're moving farther up into Aquila the Eagle. Yeah. Well, I guess we could actually we can end on this guy, on the wild duck, because that way we can show what a cluster looks like when it's not a globular cluster but looks like one. And that's what this is. There it is. Now it looks like a globular cluster, but it's actually an open cluster.
It reminded somebody of a flock of ducks.
Oh, yeah, not me.
Well, go figure.
That's okay. All right, it might be too windy to capture it right now, but we'll give it a shot. Let's zoom in, make sure we're well focused. If not, we'll just tweak it manually.
You got moonrise in about 7 minutes, Arizona.
I know. Trying to hurry up here. We probably already got moon glow on the horizon. Now, let's see, we got wind. Yeah, we got wind. Plus the stars will have to be refocused because the mirror flopped again. Okay, well, here's what we'll do. We will just do a quick 15-second shot of this and see if we can capture it. This is measure 11, by the way, guys. Oops, sorry about that. Let me get rid of this. For those of you watching on a big screen TV, sorry about that. You just got blasted with bright light. Here we are. Open cluster. And what's nice about this one is that there is a lot of dark nebula around this one. Jeez. So I gotta see here. Let's show you real quick. Look at all. This is all the dark nebula around it. Zoom out. I said this the other night when we looked in this region. It looks like you're photographing a wet driveway. But it's not. And you'll note the distinctly different color of these stars. Let's see if the color correction brings that into perspective. Here we go. That's it. And now what I'll do is I'll move this line to the left of that peak. And now that helps show more detail in here, see? This can come in. That's pretty. Let's just bring it down to just about there. So there's measure 11, and it's in a region known as the scutum star cloud. And if we come in here, and there's the scutum star cloud right here, and measure 11 is right there. Let me center it up so you can see what the field's supposed to look like. Yeah, I know. It's the last object.
What?
It's the last object, I said.
Yes.
Yes. That's the wrong thing. Yes. Well, I heard you yawn.
What?
Here's you yawn.
Oh.
Here's you yawn.
All right. Busted.
That's all right.
Cluster looks very blue tonight.
It does. I mentioned that earlier. Looks very pretty, though.
Yeah. The dark cloud below, dark cloud to the right, dark cloud to the lower left, down at the end, at the edge.
In the upper left, yeah.
Bigger one at the upper left and one to the upper right.
Yeah. And little fine tendrils here. Beautiful. Okay, we got 12 images captured here. Moonrise is, well, we can go right here. Check it out. Now, if we zoom out a little bit. Alright, we go over here. Get rid of the ground.
Moonrise will be a little north of east.
Yeah, it's right there.
Moving into Taurus.
Yeah, it's right over the Pleiades.
Yeah.
But it's going to go away more and more and more, so yeah, we're good. Yeah, the moon, according to Stellarium, is already up out there. So we're just going to get this last shot done. Okay. When our next telescope is ready in Benson, Arizona, we've already got the equipment. We are going to be doing a lot of different things with it. And one of the things we're going to do is we're going to be using it to look at the moon and the planets, because it's going to have the focal length to do that. In other words, it'll be able to magnify quite nicely. We're also going to do narrowband photography with it, where we're going to be able to capture just the hydrogen alpha, just the sulfur 2, and just the oxygen 3. What is all that? We'll explain when we get there. But those are the three components of most nebulae. And you isolate those, and when you do that photography, you see the most amazing details when you can combine those in different manners. And that's something that we'll do.
One more object.
One more?
One more.
Okay, you got a suggestion?
Saturn. Saturn is at opposition tomorrow night.
Don't know if we're going to see it.
It should be well up in the southeast.
It would be near Jupiter, wouldn't it?
Not that far, no. Jupiter's in Taurus, Saturn is in eastern Aquarius.
Well, let's go see.
So you're looking way over in the southwestern sky right now.
I know, I got to move.
There's Saturn right there.
Yeah, let's see what its elevation is. Hmm, 36 degrees in the southeast. Might be problematic, but let's try it. Why not? Okay, I will save.
Saturn at opposition means it rises at sunset, it crosses the overhead meridian at local midnight,
Right.
and it sets at sunrise. And this is, as a general thing, when the planet is closest to us, because we're on the same side of our orbit around the sun as Saturn is. You can draw a straight line between the three of them at opposition.
Oh, yeah.
From the sun to Earth to Saturn, in this case. And it is generally closest, biggest, and brightest at this time, which is why it's nice to look at planets when they're at opposition.
Nice. All right, so let's
Now,
go.
how much will we see? I don't know. This is a short focal length, wide field instrument. The rings of Saturn are closing right now. They're almost invisible, but they are still making a line across the face of the planet. Will we see it or not? I don't know yet.
I don't either. I don't know if we're even going to see it because at 36 degrees up, it's possible that it's not going to be high enough to get us over this wall of the building right here. But we can try swinging around to the other side of the sky. It may end up looking into the wall. Yeah, it's doing a little bit of that, but maybe we'll capture some of it. There it is. That's Saturn right there.
Well,
And you can see it has a streak on it. That's the wall of the building interfering with it. But let's just check it out. What we do is we actually look at it with very, very fast exposure, and we take this gain way down.
I see at least 2 or 3 moons already.
Yeah, one of them will be Titan.
Yeah.
Yeah, there we go. Let's bring it down. There we go.
When we see a planet at opposition, it's just like seeing a full moon. A full moon, by definition, is at opposition. It's 180 degrees across the sky from the sun. Rises at sunset, across the meridian at local midnight, sets at sunrise.
All the outer planets do that.
Yep.
Okay, let's...
In the case of the planets, again, that means they're roughly closest to us at that time. That's not the case necessarily with the moon. The moon is actually supposed to have like 4 supermoons in a row here coming up, though.
All right, let's do this. Let's drop our exposure. (617 milliseconds). And we'll zoom in. You see the rough shape of Saturn. We're at 110. Let's go down to 150 milliseconds. And take our gain down to 0. Excuse me. Okay, there we go. That's a little better.
Yep.
And let's take it down in increments here. Yeah, Saturn's rings are becoming very narrow.
Yep.
Remember, we're looking at it with a huge obstruction. We've got this part of the wall in the way here.
Saturn takes about 29 and a half years to orbit the sun. And as we look at the planet over the course of a complete orbit, the rings open and close twice each orbit. When the rings are open at their maximum, they're actually they are bigger than the moon is taller up and down along its polar axis. That is, you see rings all the way around the planet. What we're seeing right now is spring on Saturn just about to happen. When the rings are wide open, from our point of view, or the sun's point of view, well, that is solstice time on Saturn. And when the rings close up, so they're edge on and they disappear for a time, that's when they're directly over the equator and they become invisible, literally just a line across Saturn, and they disappear for a while. That's when it's equinox on Mars, on Saturn. Blah.
And interestingly, these rings that you see on Saturn don't have long to live, actually. The rings are actually going to go away. And there's a complex process going on in Saturn's orbit where these ring particles are falling into Saturn's atmosphere all day, all night for years and years and years. And so eventually, Saturn's rings are going to literally just burn up in the upper atmosphere of Saturn. Because the rings were always a transient phenomena on Saturn. They were never a permanent feature. But they're permanent as far as humans are concerned.
With the possible exception of the E ring, which is created by Enceladus blowing water ice crystals out into its orbit around the planet.
Well, that's true, and that's actually it's not one of the original rings of Saturn. It was actually, well, it is, I guess, but the E ring is a little bit further out. So I guess in the same way that we have the sodium Taurus from Io around Jupiter, Jupiter also has rings, right? And those rings are going to go away at some point. Timoth Man, how are you? Tim Mothman. Queen Peachy Keen, how you doing? Thank you for coming and enjoying. Hey, like I said, we're just looking real quick at Saturn. We just checked out a bunch of other things. Let me. I don't think. Yeah, see, we're not gonna be able to stack this because it's dancing around.
Yeah.
And that's a bit of an issue. But at least we got to see it. And we're looking at it with. If you check it out, if I do this, you'll see just how big it is on our field of view here. That's the size of our field. Okay, it's 1.5 degrees wide and 1 degree tall. It's a wide field telescope. Wide field telescopes are not made for planets. The next one we have, which you already have, like I said, is going in Benson, Arizona. That one is a planetary and moon viewing telescope. And we're going to do other things with deep sky objects as well with it. So, and we're going to do spectroscopy with it as well. So pretty cool. Hey, Dead Fish, what's up?
Well, thanks for indulging me.
Sure.
Everybody did get to barely see the rings of Saturn tonight.
Yeah, but, that's true. All right, so guys, this is our last object. It was sort of like the last thing that we did. I'm going to park the telescope now. And then we'll... so you can see, you watch the telescope park. And I'll just bring us up here. All right, you'll see it says parking scope slewing, and then it'll say you can turn off the power. There we go. So I'm going to go into my program that we wrote to run the observatory, and we're going to turn off the power here. Okay, power is off, and now we'll shut the roof. So here now you'll watch the roof, you watch these two objects here, on these two screens rather, and now you'll see the roof close. Now I'm in Connecticut, and this is 2,600 miles away out in Arizona, and we're running it from here. It took a couple years to figure all that out, but we did it, and we do it for you. Hopefully, if you have a mind to, visit our Etsy store up there in the upper right corner, SkyTour shop. Okay, many of our highly processed photos are put on things like blankets, mouse pads, shoes, boxer shorts, mouse pads, and tumblers of all kinds, even lampshades. I mean, we got a really cool stuff up there, and please enjoy. And then, if you're of a mind to, I think it'd be great if you could join us and be one of our Patreon sponsors. We'd love to have you with our Patreon. You know, there are Patreon levels for everybody. We would just like to, we really have to make this work. We've been doing this for a number of years now, and I don't get a paycheck for this. Daryl doesn't get a paycheck. Izabela doesn't, but she should. Okay, none of us get a paycheck, and our other two people in the organization are Marianne Robb and Tara Diulis, and they are just marvelous and amazing. They're actually out in Mesa, Phoenix area, and so they can go out to the observatory, which is out in the Sonoran Desert west of Phoenix by 80 miles. And you have to drive 14 or 15 miles of dirt roads after you drive 2 hours of paved roads to get to the observatory. So it's not an easy thing to do maintenance. But, think about it. Love to have you. It's not necessary. If you can't do it, well, that's fine. Please enjoy all the free stuff we give you anyway. Go to skytourlive.org. That's our portal where all this stuff is there. You can see the Patreon there. You can see SkyTour Shop. You can see the imagery we took. You can get fine art, too. You can get fine art stuff as well. People buy canvas prints, giant metal prints and metal of our imagery. It's all up there, too. So you guys have a good night, and we will see you on the next time we do this.
Say goodnight, Gracie.
That's right. Say goodnight, Gracie. Good night, Gracie.
Good night, Gracie.
See you guys later. Have a good night, and we will talk again. Bye-bye.
Good night, everybody.
Bye-bye.